Hello everyone, welcome to our first lecture on Mechanics and Materials 1. In this lecture we will talk about statics of particles, and essentially we cover the second chapter of the Johnston book on statics. The topic statics will be covered in 6 lectures. We call these lectures Introduction to Statics 1, 2, 3, 4, 5, and 6. So this is the first one in the series of lecture on statics. So first, to make sure that we are on the same page and you understand the notation introduced here and for this course or throughout the semester, I need to explain what notation I'm using. And in particular, we would need to distinguish between vectors and vector magnitudes a lot. In order to introduce vectors, the book is using bold letters to show vectors, but it's relatively difficult to write bold letters. So I'm doing something like this. Instead of writing a bold letter, that's, for instance, you write a letter F with a vertical line next to it, and that means vector F. If it was B, then this would be vector B, for instance, small b, that would be vector A, vector P, and so on. So if we have a vector, we can use this notation to show that. If you want, you can also use an arrow to do the same thing, or an underline. If it's a vector between 2 points, points A and B, then it makes more sense to use the arrow, of course. For instance, you think of a vector AB starting from point A to point B, then this notation makes sense. But also you want to talk about the magnitudes of these vectors. So we need to use a notation consistent with our previous notation. So if we use a bold letter F, then the magnitudes of F could be just the usual letter F. Or if you want to be more specific or more precise, maybe you can use these 2 vertical lines on the sides to show the absolute value of the vector or the magnitude. Again, you can also do it in this way or this way. If it is a vector between 2 points, again, you can use this absolute value convention, or you can just show the line AB as a distance between A to B, or the line piece AB, which is indeed the magnitudes of the vector AB. Okay, now that we know the notation, we will proceed with the next topic. And remember that throughout the semester, usually I'm going to use these two. So the next topic is statics. What is statics? Statics is essentially the equilibrium of bodies. So if you want to talk about a body in equilibrium, you would say it's statics, as opposed to dynamics, that is talking about the bodies in acceleration, in motion with acceleration. So here in statics, we are talking about equilibrium of bodies essentially, and talking about equilibrium, you usually think of equilibrium of forces and equilibrium of moments. Equilibrium of forces means the sum of forces acting on a body must be 0. So the vectorial sum of forces must be 0. And you can see this is a 0 vector. So I'm writing it like this as being bold. And if you want, this is a 0 vector in 3D. It would have 3 components, for instance. Equilibrium of moments would also be written in a similar way. That would mean that the sum of moments with respect to a point O is also 0. And then again, this is a 0 vector. Note that in contrast to F, that you can always write the sum of forces, when you want to write the sum of moments, you always need a point with respect to which you write the summation. In this case, we write the sum about a point O. However, if this equation is satisfied, so if the moments are in equilibrium, are in balance, and if all the forces are in balance, then it doesn't matter with respect to which point you are writing the equilibrium. More specifically, you can always write equilibrium with respect to an arbitrary point A, and then if this is satisfied, this would also mean that equilibrium with respect to O is satisfied, and vice versa. Okay, now that we know how to write equilibrium and how to impose equilibrium, we need to know how to deal with forces and moments on a body and how to gather them all together. For that matter, we draw the so-called free body diagram, and we use the abbreviation FBD. That essentially means that you are drawing the body and you draw all the forces and moments acting on the body, and basically that would be your free body diagram. Once you have the free body diagram, you need to impose the equilibrium equations. So basically, statics is a two-step process. Step 1, you draw the free body diagram. Step 2, you impose equilibrium on that free body. Now, in order to impose equilibrium, again, you need to remember that equilibrium means equilibrium of forces and equilibrium of moments. So they are going together. In a three-dimensional problem, equilibrium of forces gives you 3 equations, equilibrium of moments gives you additional 3 equations, and altogether they give you 6 equations. And this is for a three-dimensional problem. Okay, so in 3D you would get 6 equations. For a two-dimensional problems, equilibrium of forces gives you 2 equations, equilibrium of moment gives you 1 equation. So overall you get 3 equations for a two-dimensional problem. Okay, so that's all about statics. I need to talk a little bit about vectors themselves, and then we will go to some examples. So if you think of a vector in a two-dimensional space, a vector f is composed of 2 components, fx and fy, and you can think that fx is essentially the projection of vector f in the x direction. So you usually need to identify a coordinate system, and then you need to project your vectors on that coordinate system, and you can write that vector in terms of the coordinate system itself. In this case, for instance, if you think this is the coordinate system, then you know in the x direction you have the unit vector I, and then in the y direction you have the unit vector j. So then using this you can say, well, vector f is essentially the fx component, the x component of the force, or vector f, in the I direction, plus the y component of the vector f in the j direction. Okay, so it's again important that you see these are essentially scalar values, these are magnitudes in their own, but then they get the direction, they learn about the direction because they are multiplied by unit vectors. You can also think of this projection using the angle alpha. So if you draw an angle alpha between a vector and coordinate system, you can do the projection using trigonometric relations. In this case, fx is f cosine alpha if the alpha is this angle, and then fy would be f sine alpha. Now, if you put this into this equation, you can say that the vector f is f cosine alpha in the I direction plus f sine alpha in the j direction. You can also think of the norm of the vector now that we have this. So the norm of the vector f is square root of fx squared plus fy squared. So the norm of the vector f would be essentially this length. That would be the magnitude of vector f. And if you think about it, you can write that as f squared cosine alpha squared plus f squared sine alpha squared. And that would be just f, because we know that cosine alpha squared plus sine alpha squared is 1. You can also think of the angle alpha itself. If you are asked to calculate the angle alpha for a given vector components or for a given set of vector components, you can think of it this way, that tangent of the angle alpha is sinus alpha divided by cosine alpha, Now, if you multiply the numerator and denominator by f, you get f sine alpha divided by f cosine alpha. So in that case, you can say the tangent alpha is nothing but fy over fx. Now that we know how to handle one single vector, we can also think of a combination of vectors, or the summation of vectors in this case. So if you have a vector p and a vector q, the sum p plus q is also a vector, and in order to calculate that vector, you can use the graphical representation, or the so-called parallelogram rule. That means you start from the beginning of the first vector and you keep adding the other vectors until you finish the summation, and then the resulting vector is the summation vector. But also, using what we just learned previously, you can do it in a more mathematical way. For instance, if you think that this is the vector p itself, it has two components, px and py. Vector q itself, it also has two components, qx and qy. So if you think about it that way, you can imagine that the vector p plus q, it has an x component, and the x component of the p plus q, and this is what is shown here. So the x component of the vector p plus q is the x component of vector p plus x component of the vector q. So this is px, this is qx, and if you sum them up, you get essentially this length, which is p plus q in the x direction. You can do the same thing in the y direction. So p plus q in the y direction is p in the y direction plus q in the y direction. And again, you can think of it as this. Okay, so this is the summation of two vectors, and you can write this more elegantly, maybe like this. You can say the vector p plus vector q is px in the I direction plus py in the j direction and the y direction, plus qx in the I direction plus qy in the j direction, and then you add the x components together, you add the y components together, and you just get the results that we talked about. Now that we know how to add two vectors, you can also imagine that, let's say, instead of adding p plus q like this, we could also add q plus p. And it turns out whether you do p plus q or q plus p, you get the same vector. So for that matter, you can say that the vector addition is commutative, and basically it means that p plus q is the same as q plus p. Now, if you want to subtract two vectors, you can also do the same thing. So q minus p is nothing but q plus minus p, whereas minus p is the same vector as p in the opposite direction. So if you have a vector p, then the inverse of that, or minus p, would be exactly the same thing in the same line in the opposite direction with the same magnitude. And usually, if you talk about p plus q, we may use the letter r to show that this is the resultant force. So the term resultant is appearing frequently in this course also. And also, graphically, if you wanted to show vector q minus p, again, it looks like this. It's a vector starting from q. It goes in the minus p direction, and then this would be q minus p. So that was that for two vectors. Now, if you have more than two vectors, what we do? For more than two vectors, you can always split them into pairs of two vectors. So for instance, if you can think of p plus q plus s in this example, you can first do p plus q. So you get the blue line, it's two vectors, so it's easy. And then once you have p plus q, you can also add s to it. Okay, so you get p plus q plus s. But also you could do it in a different order. You could first do q plus s, and then you can add p to it. Again, you end up with the same vector, p plus q plus s. So this follows from the summation of vectors being commutative. So whether you say it's p plus q, then plus s, or you say it's p plus q plus s, it's the same thing. It's always p plus q plus s. So that's all we wanted to know about notation, about vectors. This was just basically an introduction to what we want to do. Now, equipped with that, we want to go to some examples. We would like to look into some exercises together, and then after that, we will talk about statics in 3D. So the first exercise that we want to look at is similar to the exercise or to the problem 2.6 from the book on page 39 and the 9th edition of the Beer-Johnston book. In this example, we see a boat. This is essentially the boat. It's in a test channel. The test channel has a flow direction as shown, and basically this flow wants to push the boat in the same direction as the flow. However, the boat is kept in equilibrium by keeping point A at its place using 3 cables. So we have a cable AC, AB, and AE. Using these 3 cables, we don't allow this boat to move, and the dimensions are shown here. So this length is 7, this is 1.5, and this height is 4 meters. This is also 4 meters. So for the boat in equilibrium, we know that the tension in cables AB and AE are 200 and 300 newtons respectively. So that means you have a force here in AB, and that is 200 newton, and then you have a force here on AE, and that is 300 newton. Now, pay attention that I draw the force like this because we know these are cables, and cables and ropes, they can only carry tension. So they cannot push the boat, they can only pull it, if you want. You are asked to calculate the drag force. That's the force that is applied to boat to push it in the flow direction, and also to calculate tension in cable AC. And then again, it's a cable, so we know this is going to be the direction, so that's cable AC. For any example, you always are given some information at the beginning. These are assumptions of the examples, and then usually you should be looking for a keyword like determine, and then anything after the keyword determine is something that you are asked to do. So the first thing you should remember again about this example is that the cables and ropes, they can carry only tension, and we use that to draw the directions of the force and so on. So remember, statics had 2 steps. The first step was to draw the free body diagram, and the second step was to impose equilibrium. And then equilibrium would be equilibrium of forces and equilibrium of moments. Now, equilibrium of forces in 2-dimensional problems, and this is a 2-dimensional problem that we are talking about, is equilibrium of forces in the x direction and equilibrium of forces in the y direction. We should usually also impose the equilibrium of moments with respect to a point in the space, but in this case we are talking about equilibrium of a point, of a single point, and a point has 0 dimension. So because a point is significantly small, then equilibrium of moments does not give us any additional equation. So in this example, it's not applicable, or it's not useful, it's redundant. This is the free body diagram. For the free body diagram, we consider point A, which indicates the tip of the boat. The drag force is pushing the boat in the flow direction, so that is Fd. The tension in cable AC is along the cable and in the tension direction, so it's pulling the boat. And tensions in cable AB and AE also are pulling the boats in their specific directions, and that they are given. So we know their values. We are also going to need these two angles alpha and beta, but we can calculate them from the dimensions given in the picture. So if you think about alpha, we know that this distance was 7, and we know that this height was 4. So for that matter, for instance, you know that the tangent of alpha would be 7/4, or alpha would be tangent inverse of 7/4, and that gives us 60 degree almost. You do the same thing for beta, so beta would be arctangent of 1.5 divided by 4. So we know these two angles. Now, once that we know the angles, we can write these forces in terms of their components to satisfy the equilibrium. So equilibrium of forces in the x direction is written as such. If you assume this is the positive direction, so if essentially that means the coordinate system is chosen like this, so if the x direction is positive, and then for the y direction we assume upward is positive, then you can see FD is in the same direction as the positive x direction, so it's essentially appearing with a plus sign, so it's FD. AC, the x component of that, is also appearing in the positive direction, so you get TAC times sinus beta, and then again, remember this is essentially TAC sinus beta. For TAB, you can see that TAB sinus alpha is in the opposite direction, so for that matter, you get a minus sign here. You can also write the equilibrium in the y direction. For the y direction, you can see that TAC in the y direction, it would be TAC cosine beta, and that's upward, so it comes with a plus sign. TAB in the y direction is also upward, so that's TAB cosine alpha. TAE is downward, so it comes with a minus. So that's all you have for your equilibrium equations. Now, looking at what you know and what you don't know on these equations, you can see that sinus of beta and alpha and cosinus of beta and alpha are known because you know what are alpha and beta. AB and AE are also known. What you don't know is TAC and F. So you have two unknowns, two equations, and you can calculate the values for TAC and TAB. If you do that, TAC would be 214.5 Newton and FD would be 98.3 Newton. Okay, so that is example 1. We look into a second exercise. So exercise 2 is similar to problem 2.3 on page 44 of the Beer-Johnston book on statics. This problem shows a collar A connected to a weight via a cable, and the collar A is mounted on a frictionless rod, and it can move in the horizontal direction free of friction. So you can imagine if there is a weight here, the rope is pulling the collar A, so it wants to essentially pull the collar in the horizontal direction towards right, but you need a force to keep it in balance. This is essentially what's happening. So for this problem definition, you are asked to calculate the force P, or the magnitude of force P, such that this equilibrium is satisfied. Again, similar to the previous problem, we start from our usual assumptions. or usual steps, the first step is to draw a free body diagram. The second step is to impose the governing equations, the balance equations in this case. Also, for this problem, we will need to use the angle alpha. In order to calculate the angle alpha, we use the dimensions given in the problem. If you think of this height as 400 millimeter, and then this is 300 millimeter in the horizontal direction, then this triangle that we have here is similar to the famous triangle with the dimensions 3, 4, 5. So basically it means that the length here would be 500. And therefore, the cosine of the angle alpha is 3 over 5, and sinus of the angle alpha is 4 over 5. Again, we need to start with a coordinate system. We usually assume the coordinate system as such, so we assume that the x is in the horizontal directions towards right, y is the vertical directions upward. But if you want, you can choose any coordinate system, but you need to show it for each example specifically to make sure. Now, the free body diagram looks like this. So if you think of a point A or color A as being a point, you have a tension applied to it. You have a force from the rod, the vertical force from the rod applied to it, and then you have the force P keeping it in its place. Now for this force combination, you can write the balance equation sigma Fx is 0, sigma Fy is 0. In the x direction, you can see the force P is in the negative x direction, so it appears with a minus sign. And then T, or the x component of T rather, it's T cosine alpha, and it's towards right, so it appears with a plus sign. Now in the vertical direction, you have T sinus alpha, upward direction, and then you have N also in the upward direction. Again, you have two equations, two unknowns, and if you assume that the T in the cable, the tension in the cable is 200, so remember this is 200, so this is our cable, and this is essentially a common pulley. Assuming that T is 200, you have two equations, two unknowns, so we don't know what is P, we don't know what is N, we know what is alpha, and assuming that T is 200, it's a two equations, two unknown, you can calculate P and you can calculate N. Now for N, you can see that it appears with a minus sign. That means the direction that we assumed here, it's wrong, so it shouldn't be upwards, and indeed it means that N is downwards and 160 Newton, which also makes sense. If you think about it, if the tension in the rope is in this direction, you need a vertical force downwards to keep this piece in equilibrium. Now, the question is, why we assume T is 200? How do you know that the tension in cable is 200? The common answer and the common mistake is that we think it is 200 because it's the same rope or it's the same cable. This is not correct. So if you want to think why T is 200, we should never say that P is 200 because it's the same rope. And I try to explain that in what follows. It's only 200 because of the equilibrium of pulley. So remember, if you have a pulley like this, now you have a force T downwards, and then you have another tension here. The distance from the center for both of them is R, and the angles are 90 degrees. This is important. So if you look at this and you say, well, I am going to write the balance of moments with respect to point B, then the balance of moment with respect to point B reads TR equals T1 times R. And then because the r's are equal, the radius, the distance from B is equal, then T and T1 are equal, and then T is 200. In particular, if you want to make a difference, you should look at the yellow part of the example. So here. So if you think about a pulley where the force T1 is applied on the outer circle and the force T is applied on the inner circle, you can imagine in this case the inner circle has a smaller radius than the outer circle. So you need more force, you need more tension to keep this pulley in equilibrium. So in this case, because tension is applied to a smaller circle, then it's more than T1. You can also compare it with the other example here. If the force T1 is applied on the inner circle and then T, the tension that you apply, is on the outer circle, that means you need less tension to keep that in equilibrium. So essentially this is a concept that is used to design pulleys and to design systems that take advantages of the properties of pulleys to keep equilibriums in systems with less forces. So usually you want to keep something heavy with less force, you can always use this concept. So far we talked about vectors in 2D space and we saw two exercises to understand those. Now we want to talk about vectors in 3D space. So in a 3D space, a vector f has three components, fx, fy, and fz. In order to better understand these components, we can think of them in two ways. The first way is more similar to what we did in a two-dimensional problem, and the second way is more similar to what we do in what follows. So if you think of a vector f in a 3D space, you can think that it has an angle theta y with the y-axis. Now using that angle, you can project that vector f into the xz plane, so into this plane. On this plane, you can see that the vector f has a component fh. Now looking at that component fh or that vector fh itself, you can see that also creates an angle phi with the x coordinates, and therefore you can have the projection of fh into x coordinate, and that therefore fx would read fh times cosine of that angle. If you want to think of fz, it also means that fz is fh times sinus of that angle. So having said that, we can also think of a vector f and its angles with each vectors or with which direction separately. For instance, if you think of a vector f, it has an angle theta x with direction x. That means fx would be f times cosine theta x. If now you think of the y component of the vector f, you can think that fy is f cosine theta y. And eventually fz would be f cosine theta z. Similar to what we did in 2D, a vector f can be written as the sum of its component in three directions. So it would be the x component in the I direction or in the x direction plus the y component in the j direction. So this would be essentially the unit vector in the j direction, and then the fz component in the z direction, obviously, and that is shown using a unit vector k. Based on what we learned, therefore, we can write fx, fy, and fz as such. So it would be basically the vector f times cosinus of the angles theta x, theta y, and theta z, respectively. Now, using these three relations into the definition of the vector f, you can write the vector f as the magnitude of vector f times its direction. And now basically its direction would be cosine theta x in the I direction, cosine theta y in the j direction, time plus cosine theta z in the k direction. Now again, we call this the direction because if you think of the norm of the left and the right hand side, you can see that the norm of f, or the magnitudes of f, would cancel with the right hand side, and therefore you know that the magnitudes of what is left, or the magnitudes of this big term is 1. In other words, that means that term is just a unit vector. Now, knowing that this is a unit vector, you can say that the vector f is just its magnitude times its direction. So remember, we just said it's a direction. So basically it shows the direction, and we can call it a director. It is a usual notation for showing the direction of the vector, and it is something similar to unit vectors I, j, and k. So again, I, j, and k, they show the direction with respect to x, y, and z coordinates. Now, this one shows the direction of a vector along itself. And basically, you can write that director vector as cosine of theta x in the I direction, cosine theta y, j direction, cosine theta z in the k direction. Putting that all together, you can say the vector f is its magnitude times its direction, and it's shown here. So this is a vector f, and you can think of its magnitude as this little vector with the unit length. So it has a magnitude 1. And that unit vector itself, it has 3 components in terms of the x, y, z coordinates. So the director lambda has 3 components: lambda x, lambda y, lambda z. Again, the norm of lambda, we know it is 1, or the magnitude of lambda is 1. And the 3 components, lambda x, lambda y, and lambda z, can be written in terms of the cosine of the angle. So lambda x is cosine theta x, lambda y is cosine theta y, and lambda z is cosine theta z. If you think of what we had in the previous slide, basically it means lambda x is the ratio of fx over f, lambda y is the ratio of fy over f, and lambda z is the ratio of z over f. Putting all this together, you can then say, well, we know now lambda components are written as such, and then we know the norm is 1. If you put this together, you can imagine that then the norm of lambda, the magnitude of lambda, is square root of cosine squared of theta x, cosine squared theta y, plus cosine squared theta z, and you know that must be 1 altogether. So basically it tells you you have this identity. Now, how this identity in 3D, so this is a 3-dimensional identity, how this identity in 3D would reduce to a 2-dimensional identity? That's what we want to answer. We want to know how to reduce this in 2D. Now, if you think about 2D, you should think of the vector as this. So if we zoom into that, you can see that in 2D, a vector that would be usually like this in 3D, in 2D, a vector stays on the xy plane. So if you have a vector only in the xy plane, that means the theta z angle, the angle with the z axis, is 90 degrees. But also it means that you have these two angles, theta x and theta y, on the same plane of xy. Now, using this information, if you assume that theta z is 90 degrees, that means cosine of theta z is 0. So this relation, this 3D relation, reduces to a 2D version of it. So the 2D version of that is this. Now, since we know in 2D, theta y is 90 degrees minus theta x, we can also simplify that. So if you insert theta y equals 90 degrees minus theta x, and you use the identity that cosine of theta y is cosine 90 minus theta x, and then cosine of 90 minus angle is the sine of the same angle, you can say cosine theta y is the sine of theta x. So for that matter, this relation is nothing but this very famous and well-known direction. So well-known relation, cosine squared theta x plus sine squared theta x is 1. So this relation that we had here is a three-dimensional version of this relation, essentially. So this is 3D, this is 2D. Again, none of what we did is substantially new, but it's important that you have a good feeling about it and good understanding of it to be able to solve the problems that come. Now, if you want to think about a vector between 2 points A and B, so let's say you have a vector between 2 points A and B, vector AB, you can also think of writing that vector AB, in terms of its magnitude and its director. If you want to do that, you should calculate the magnitude and vectors and the direction separately. The direction can be written as the vector divided by its magnitude. And it's fairly simple how we get this. This relation is nothing but this. Remembering that the magnitude of AB is scalar, you can just divide this relation by that scalar value, so you know that the vector AB divided by its magnitude, so you may call it the normalized vector AB, is exactly the direction. So lambda AB is the director from A to B. It has three components, lambda x, lambda y, lambda z, in ij k direction, and it can be calculated easily using this formula. If you want to write it in terms of coordinates, you can also do that. So lambda would be written as such, and then again, this we have here in the numerator is essentially the vector AB, and then in the denominator what you have is nothing but the norm of the vector AB. And using that you can write the 3D vector. Okay, so far we know how to handle the 3D vectors. What we want to do is to go to some exercises, and we want to better learn how to use what we just have learned about vectors in 3D to solve a few examples. In particular, we will look into two examples in what follows. So we are looking into the third exercise in our first lecture. This is similar to problem 2.7 on page 50 of the Johnston book. The structure shown in the picture is given and it's in equilibrium, and we know that the tension in the wire is 2500 Newton. And then again, you should always look for the keyword determine, and everything after the word determine is usually what you need to calculate. You are asked to calculate the components of the force acting on bolt A. So there is a force here on bolt A, and you are asked to calculate its components. You are also asked to calculate the angles, theta x, theta y, theta z, defining the direction of the force. So this force, we want its magnitude and its direction, its angles. So in order to do that, we start by analyzing the structure and what we have. The first thing that we can do and we must do is to define a proper coordinate system. So we assume this is the coordinate system. So x is in the horizontal directions towards right, y is pointing upwards, and z is pointing in the direction out of the plane, essentially. We also need to set an origin for the coordinate system. So we assume the origin is point O and the coordinate is 0, 0, 0. Now, based on the origin coordinates, we can write the coordinates of point A and point B. If you do that, you can see that point A is coming 40 meters towards right. So x is 40. It's in the same plane, in the same xy plane, so it doesn't lift horizontally. That means the y coordinate is 0. But in the z direction, it's as if point A is going in the opposite direction, is behind the axis x. That means the z coordinate is minus 30, and the distance is 30 meters, obviously. Now you have a tension in the cable 2500. The coordinates of point B is also given here. If you look at point B, it's exactly on top of the origin. That means the y coordinate is only different from the origin, but the x and z coordinates are the same, so these two are exactly 0. So that's what we need. We need basically the coordinates of the two ends of the rope first. Then we can think that the tension in the rope, in the cable, is TAB. Now that tension vector, this is a vector, it has again a magnitude which is TAB, and it's shown as 2500, and then it has a direction lambda. Now direction lambda, it can be written as vector AB divided by the magnitude of vector AB. So you remember the vector AB is essentially is the coordinates of B minus coordinates of A. So if we want to do that, for instance, you can imagine that the x coordinate of vector AB would be bx minus ax. Similarly, if you think about the y coordinates of vector AB, it's by minus ay, and the z coordinate of the vector AB is just bz minus az. Now, if you do all this, you can see that x coordinate is minus 40 because it is 0 minus 40, so you get minus 40. Then you have 80 because it's 80 minus 0. And then you have 30 because it's 0 minus minus 30. So remember again, this is plus 30 because it's minus minus 30. Now you know what is vector AB exactly, and using that you can also calculate the norm. The norm would be 94.3 meters. Okay, once you have that, then it's fairly simple. All you have to do is to insert this into this equation. So you then calculate TAB, and TAB would be given as such. And remember, this was the first thing that you were asked to calculate. You were asked to calculate the individual components of the tension, and this is what you have. So the x component is minus 1050, y component is 2100, and z component is 800 Newton. These are exactly these three components of the force. But also you were asked to calculate the angles that the force makes with the axis, essentially. So in order to do that, remember the angles theta x, theta y, theta z, they follow this relation that the cosine of the angle is the component of the corresponding direction vector. So cosine of theta x is lambda x, cosine of theta y is lambda y, and cosine of theta z is lambda z. And then you also remember that each of these is calculated by dividing that component of the force divided by the force itself. So here we can do that. So you know fx divided by f, or you can think of it just in terms of the components of the lambda itself. So in this case, it would be abx minus ab. So you can also think of it as a ab in the x direction divided by the norm of ab. If you do that, you get also the same answer. So once you know these components individually, you can use the inverse of the cosine function to calculate the angles themselves. If you do that, then theta x, theta y, and theta z can be calculated. Also, I need to emphasize that you should remember that when you use the cosine inverse function of something, it then usually means that the angle itself is between 0 and 180. The next exercise is similar to the problem 2.9 on page 58 of the book Johnston. In this exercise, a 200 kilogram cylinder is shown at point A. This weight is supported by two cables, AB and AC, but also in order to keep equilibrium in the horizontal direction, in the x direction, we also apply a force P. And the force P is perpendicular to the wall. So this angle is essentially 90 degrees. You are asked to calculate the magnitude of P and also tension in each cable. Similar to the previous example, we need to analyze the geometry of the problem first, and we draw the free body diagram. So we know the mass of the hanging weight is 200 kilogram. So the weight itself is a vector downwards. So in the opposite direction of the y direction. That's why we have a minus. And then it's mass times gravity. So for gravity, if you assume 9.81, then the weight would be minus 1962. And then again, minus just means that it is in downwards direction. It's in the opposite direction of the y-axis. So that's that. Now we need to look into the tensions in the AB and AC. Again, you remember AB and AC, these are cables or ropes, and they can only carry tension. They cannot push the point A. They can only pull. So because they have that property, we know already the directions and we can draw them like that. But also we know the direction. They are always along the cable. Okay? So TAB would be along the line AB and TAC would be along the line AC. For that matter, first we calculate AB and AC. And it's very simple. So again, if we do exactly the same thing like we did before, we know that AB is essentially subtracting the point A coordinate from point B. So AB in the x direction would be BX minus AX and so on. And the same holds for AC. This is a relatively simple structure. So once you do that, you can see that AB would be minus 1.2 in the x direction. So you can, for instance, look at this. Point A is here, point B is on this plane. So the distance between them is 1.2 and point B is behind point A if you think of the x coordinate. So there is a minus, and then the same thing holds about the other directions. If you think of the y coordinates, point A is here, point B is here. So point B is above point A in the y coordinates. The whole height is 12 meters, and we know this little distance is 2 meters. It's given here. So therefore, you know that what is remaining is 10 meters, and therefore this is 10 in the j direction. The same holds for the k direction. If you think now about point A, in the k direction or in the z direction, point B is 8 times ahead of point A. So you calculate AB and AC similarly, and using that you can also calculate the directors of AB and AC. So the director of each is calculated using the vector divided by its magnitude. If you do that, then you can write the vectors in terms of their magnitudes and their directions. So vector AB is the magnitude of AB, or the tension vector in the AB direction. So this is a vector, is the tension magnitude times the direction. tension vector in the AC direction is tension magnitude times the direction. So all you have to do is then satisfy the equilibrium. For equilibrium, again, we write the equilibrium of forces, and again, because we are talking about the point, equilibrium of moments does not provide any additional information. Equilibrium of forces, it's written as such. That means sum of F in the x direction is 0, sum of F in the y direction is 0, and sum of F's forces in the z direction is 0. So this is essentially three equations. What we can write it as one, and that would be tension vector in the AB plus tension vector in the AC plus P plus W weight is 0. And then again, if you look at the picture, it's very clear. You have point A, you have tension AC, tension AB, P, and weight. You have four components acting on A, and you just add them up. You set that to 0, and if you look at what is unknown and what is not known, you know that the tension in AB and AC is not known, and also you know that the P is not known. However, you know the direction of P. You know that it's in the horizontal direction, it's perpendicular to the wall, and it's in the x direction. So you know it's in the I direction. So this is essentially three equations, and you have three unknowns. And obviously, once you have a system of three equations, three unknowns, you can calculate the answers. P would be 235 Newton, TAB would be 1402 Newton, and TAC would be 1238 Newton. Okay, so this was the last example for this lecture. In this lecture, we wanted to talk about statics of particles, and again, we covered chapter 2 of the Beer-Johnston book. This was the first lecture in our Introduction to Statics lecture series. We have 6 of these, and 5 of them are yet to come. See you in the next lecture.